On July 1, 2025, a telescope in the Chilean desert flagged a moving object that didn't belong. Its trajectory wasn't a gentle ellipse, the kind every planet, asteroid, and comet native to our solar system follows. It was a hyperbola, a path so steep and so fast that nothing gravitationally bound to the sun could ever produce it. Whatever this object was, it hadn't come from anywhere near here. It was passing through, and within days, it had a name. 3IATLAS. Only the third interstellar object ever confirmed entering our solar system. That alone would have been enough to make headlines. But over the following year, as telescope after telescope turned to study it, 3I Atlas kept doing something stranger. It kept refusing to behave like anything astronomers had catalogued before. Let's start with the basics. The I in its designation stands for interstellar, and the number 3 simply means it's the third object of its kind ever confirmed, following 1I, Oumuamua, discovered in 2017, and 2I, Borisov, discovered in 2019. The Atlas comes from the network of telescopes that first spotted it. The asteroid Terrestrial Impact Last Alert System. 4 automated telescopes in Hawaii, Chile, and South Africa that scan the entire sky multiple times every night, primarily hunting for objects that might one day threaten Earth. This time, they caught something that had traveled here from an entirely different star system, moving at roughly 58 kilometers per second relative to the Sun, faster than either of the 2 interstellar visitors before it. Its orbit made the interstellar origin undeniable almost immediately. Astronomers around the world confirmed it within days, and a research team, led by scientists at Michigan State University, rushed out the first scientific paper on the object before the month was even out. From the beginning, 3I Atlas behaved like a comet. As it approached the sun, it developed a coma, the glowing envelope of gas and dust that forms when solar heat begins vaporizing ices near a comet's surface, and a faint tail streaming away behind it. In August of 2025, the Hubble Space Telescope captured that early activity directly, imaging a dust plume being ejected from the sun-warmed side of the nucleus. Straightforward enough so far. Comets do this. It's what comets are for. Then the chemistry started coming back, and things got considerably weirder. NASA's James Webb Space Telescope observed 3I Atlas in August of 2025, using an instrument capable of splitting incoming light into a detailed chemical fingerprint. What it found immediately stood out. The comet's gas envelope was dominated overwhelmingly by carbon dioxide, accounting for roughly 87% of the total mass being released as gas, compared to only about 4% from water vapor. In a typical solar system comet, water usually dominates that mix by a wide margin. 1ATLAS was doing almost the opposite. Around the same period, NASA's Swift Ultraviolet Optical Telescope caught the comet actively releasing water as well, detecting the faint ultraviolet glow of hydroxyl, a byproduct created when solar radiation breaks apart, water molecules escaping from the nucleus. So water was there, it just wasn't the main character in this comet's chemistry, the way it usually is back home. Then, in November and December of 2025, two X-ray observatories, XRISM and XMM Newton, turned their instruments toward the comet and detected something that had never been captured on an interstellar object before: a diffuse X-ray glow surrounding the nucleus, most likely produced when charged particles streaming from the sun collide with the comet's expanding cloud of gas. It made 3IATLAS the first interstellar comet ever observed in X-ray light, adding yet another first to a growing list. But the strangest discovery was still coming. After 3IATLAS swept past its closest approach to the sun, Webb observed it again in mid-December and then once more later that month, this time watching how the comet's chemistry evolved as it cooled and moved back outward. Water production, as expected, dropped off fastest, since water ice needs relatively more warmth to turn to gas compared to more volatile substances. But then something unexpected showed up in the data: methane. This marked the first direct detection of methane ever recorded on an object from outside our solar system, and the amount was substantial, found at roughly 14 to 27% of the water production rate across the two observation windows, a proportion far higher than what's typically seen in comets native to our own solar neighborhood. Here's why that timing matters. Methane is an extremely volatile substance. Left exposed on a comet's surface, it should boil away into gas almost immediately once warmed, even slightly, by sunlight. The fact that it only showed up in significant quantities after the comet had already swung past the sun and begun cooling suggests it wasn't sitting on the surface at all. Researchers believe it was buried beneath an outer crust, shielded from solar heating during the comet's closest approach, only released once warmth finally worked its way down into deeper icy layers. In other words, 3I Atlas wasn't just showing off a strange chemical mix. It was slowly peeling back its own layers in front of the very telescopes watching it. Later analysis added one more twist. Researchers also detected a rare deuterated form of methane in the comet's coma, a molecule where one hydrogen atom is replaced with deuterium, a heavier isotope of hydrogen. This kind of measurement is exceptionally difficult to make, even for comets within our own solar system, and finding it on an interstellar object gave scientists their first real window into the specific chemical conditions the comet formed under, in whatever distant star system it originally came from, likely billions of years ago. Taken together, this chemistry tells a genuinely interesting story. This isn't a wanderer that happens to resemble our local comets. Its unusually high carbon dioxide content, its varied and delayed methane release, and its distinctive isotopic fingerprint all point toward an object that formed in a fundamentally different environment than anything native to our solar system. 3I Atlas isn't just visiting from another star. Its chemistry is a message, in a sense, about the conditions in the place it came from, conditions we have almost no other way of directly sampling. Now, it would be impossible to talk about 3I Atlas without addressing the elephant in the room. Almost as soon as its unusual trajectory and unusual chemistry began making headlines, a small but vocal corner of the public conversation started asking whether this object might not be natural at all. Harvard astrophysicist Avi Loeb, known for previously raising similar questions about Oumuamua, proposed a kind of tracking scale for interstellar objects, ranking how likely each one is to be artificial rather than natural. It's worth being precise here. Even Loeb's own public assessments have consistently placed 3I Atlas as most likely a natural object. A comet, not a technological artifact. Every major research team studying the comet directly, using data from Hubble, Webb, Swift, XRISM, and ground-based observatories around the world, has found behavior fully consistent with cometary activity, outgassing that follows predictable physical patterns as the comet heats and cools. Chemistry that, while unusual, fits within the range of what's physically possible for icy bodies formed in other star systems. Nothing detected so far requires anything beyond ordinary comet physics to explain. The genuinely fascinating part isn't a hypothetical spacecraft. It's that a chunk of ice and rock assembled around a star will likely never identify, drifted alone through interstellar space for what may be billions of years before crossing paths with our solar system for the first and only time. That's not science fiction. That's just an extraordinarily rare and extraordinarily lucky cosmic encounter. 31ATLAS made its closest approach to the Sun in late October of 2025, then swept past Mars in early October, observed at close range by ESA's Mars Express and ExoMars Trace Gas Orbiter, before continuing onward. In March of 2026, it passed near Jupiter, where ESA's JUICE spacecraft, originally built to study Jupiter's icy moons, happened to have the best vantage point of any spacecraft in the solar system, catching the comet in a notably active state. Data from that flyby is still being analyzed. By spring of 2026, the comet had faded from what small telescopes could observe, continuing its long path back out of the solar system entirely, never to return. Unlike the planets, unlike even most comets we're familiar with, 3I Atlas isn't in orbit around our sun. It's just passing through on a one-way trajectory that will eventually carry it back into the emptiness between the stars. This time for good. 2 prior interstellar visitors gave us brief, imperfect glimpses of what lies beyond our own solar system's formation. 3.1. Atlas gave us, by far, the most detailed chemical portrait yet, an actual fingerprint of material assembled somewhere else in the galaxy, under conditions we can only now begin to reconstruct. We may not get another object like this to study for years, possibly decades, but newer survey telescopes, built specifically to scan wide swaths of sky repeatedly and catch fast-moving objects before they get too close to notice, mean the wait for the next interstellar visitor is likely to be considerably shorter than the wait for this one. When it arrives, we'll be ready, and whatever story its chemistry has to tell, one thing 3I Atlas has already proven is that these visitors are worth the wait. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.